Good morning, America. Okay, gentlemen, we are ready for the questions coming up from the world. So here we go. Why did EPC selected 3 by 5 millimeter or 3 by 5.5 millimeter size PQFN? I just follow a joke at that point. The tuner size in televisions had also a very strange dimension in the past. And it was based on the tobacco box of the designer who had put his circuitry in a tobacco box and then had been the one which made it for mass production. I don't think that's the way you had it, Alex.
What is it? The entire rail system in Europe is based on carriages from the Roman era because they had to be wide enough for 2 horses, right? So
absolutely. And you know what happened going to Russia? They sent the spy out measuring it. And they measured the outside of the track. And when they came back to Russia, they used it for the inside of the track. So that's the problem with the trains going back and forth to Russia.
That's crazy. Well, our reason for doing these sizes is not quite as lyrical, but the reason we picked 3 by 5 and 3 by 5.5, the 3 by 5 is for the discrete products, and it is a tiny package. And one of the big advantages of gallium nitride is it's much smaller than silicon. So we wanted to find packages that don't compromise that size advantage, and yet are very robust and have wide enough lead spacing. So that was the 3 by 5. And then in order to accommodate many more leads for the ICs, we extended for the IC package to 3 by 5.5. And the net result is we have packages that don't add any significant inductance, they don't add any resistance, and also they are thermally as efficient as a chip scale package, which was very difficult to achieve.
Okay, Alex. Let's see, there is another question coming in. My backstage is feeding us. This question goes to Amitava.
That's me, Amit. Yeah, you can call me Amit. That's easier.
Amit is easier. I tell you, when I worked for RCA GE Harris, I had a colleague, his name was Jack Voislavovich, and they all called him Jack W, because most of the colleagues were not able to spell his last name. So what will be some of the hot issues in GaN in 600-volt domain?
Yeah, in fact, speaking of the name, in fact, earlier, we had a governor whose last name was Blagojevich. So whoever complains about my name, I just tell them that just look at Illinois governor's last name. So mine is easier.
Yeah, Blagojevich.
Yeah, yes. Basically, GaN, 650-volt GaN and has come off a long, hard road. So now I think we're in a position that is a fairly stable technology, and and also people have now shown, and including Tagore, the reliability is pretty good. We have done all the testing that needs to be done in the lab, such as like all the JDEC testing and additional testing that's recommended by JC70 group. We have done a lot of accelerated testing. Now, the hot issue right now is really to kind of see how the GaN behaves in the field, right? So lots of parts are in the field, and so far the reports are pretty good. So I would say the number one concern that we see from the customer is the reliability, especially the field reliability, and they're slowly accepting that, look, GaN is reliable, and as the time goes by, I think there'll be more acceptance. All our lab test shows that GaN is very reliable. It's a wide bandgap material. So that's one hot topic, the reliability, right? And then in terms of the efficiency, GaN GaN has been, historically GaN has shown to be more efficient, that means less loss. So that enables a smaller heat sink and essentially enables you to make a more compact power supply. There's plenty of data on that, so that's kind of a settled issue, right? And third is cost, and the cost is coming down. Maybe at some places it's coming down too fast for us, but the cost also is now very much it's a very reasonable cost. So reliability, and then efficiency, and the cost. They're the three hot topics. And as time goes by, I think we'll see a much wider acceptance of GaN, because as the field data will come in, and it will show, as our lab data shows, that GaN is a very reliable material, and we just have to be careful to weed out the defects in various screening. That's really our job, and we are putting in place various mechanisms to take out the defects that could be there. But overall, the situation looks pretty good.
Thank you, Amit. We are ready for the next question. This question is to all of you. Have you seen GaN applied to automotive applications such as inverters, onboard chargers, and converters as power devices? I think that's quite a challenge.
Maybe I could also go through the history of that.
Okay, Alex, that would be nice.
Yeah, the first application for GaN in automotive was actually headlamps, and that dates back almost 9 years. And they're on headlamps today all over the world. And then the second application was really not a commercial application, but it was LiDAR sensors. And today there are hundreds of thousands of LiDAR sensors on vehicles, not just autonomous cars, but in China there's quite a widespread adoption of LiDAR sensors for blind spot detection, as well as forward and rear detections. And then the third application that's starting to come in right now is DC to DC converters for 48-volt systems, like you hear on mild hybrid cars or even electric cars, where they're going to 48-volt systems because the electrical loads are increasing for all of the accessories, including things like steering and suspension, pumps and fans and heaters and stuff like that. And then, there's also a application in onboard chargers for electric vehicles. And then there's a big question mark, and I will stop there, but with the question mark being, what about the traction drives, the EV drives, which today are dominated by either IGBTs or silicon carbide? And I'd say that's a big opportunity potentially for GaN, but maybe it's also a false opportunity where silicon carbide is a better choice.
I agree at that point, Alex. I hear a little bit about vertical GaN, and if vertical GaN becomes a reliable source and is able to serve higher voltage classes, then it might fight at that point with silicon carbide in the inverter. And as the automotive drivetrains are going up to 800-volt systems, then we need really, really high voltage GaN, and that would be probably only in the vertical GaN arena become possible. That's just something I like all of you the opinion to what I just mentioned about vertical. If you see things coming up there.
So one topic on that, what Alex already said about automotive, I just want to add that the onboard charger is essentially is a very good candidate for GaN, and you will see a lot of applications. There are cars, actually some supply vans which are using GaN onboard charger, and by 2025, 2026, you will see a lot of GaN onboard chargers. That's I think is given. Besides what Alex has pointed out. Now, in terms of the 1200 volt, vertical GaN is in the early phase of development. So I'm not too familiar with the current status, but we expect to also do lateral GaN 1200 volt, let's say by sometimes in the 2025 around that time frame. You'd also see actually 1200 volt lateral GaN, slightly differently architectured, and that actually will be suitable for the 800 volt battery system. But I just want to remind that the majority of the cars are still 400 volt system as of now, and as they're pushed to smaller electric vehicles, we have to see how this 400 volt system and 800 volt system, how they kind of pan out. It is something to be watched. So in summary, OBC is already a good domain for GaN, and you'll see. And 1200 volt GaN, lateral GaN is coming fairly soon. And vertical GaN, we have to kind of, it's an early phase of development, and you have to see how it pans out.
If, just for my understanding, having 1200 volt lateral GaN and being avalanche proof, you probably have a 1700 volt device that you rate down to 1200 volt.
Yeah, so those details are yet to be kind of tested, but it won't be GaN on silicon, that for sure. 1200 volt.
Okay. So we can go for the next question. What are biggest potential domains for GaN in future where no other semiconductor can survive?
So I think there are a couple of opportunities. One of them, which we're already realizing, is space. And gallium nitride devices, particularly if they're made in enhancement mode with a p-GaN gate, are really immune to radiation effects, whereas silicon MOSFETs are extremely sensitive to those radiation effects. So EPC is a whole division, space division, which makes GaN for satellites. And just recently, a couple of the key satellite manufacturers, major corporations that make a lot of the satellites, they said that they're not doing any more silicon designs in power. that they're all going to GaN. So I think that's something that GaN can do that silicon can't. I think there are also opportunities as yet unrealized in high temperatures where wide band gap in general, because of the wide band gap, is less sensitive to temperature effects. And things like downhole drilling for wells and oil wells and geothermal applications is another very good one. So in general, I think GaN can do that. The third area is it can make things much, much smaller. So it can go where silicon can't go. And just an example that I have that in Europe you can now access is this X-ray machine that actually sits inside a pill, and you can actually take this in Europe. It's approved. This is for a colonoscopy. It has a little X-ray machine in it, and you can't do that with silicon for a lot of reasons. But that X-ray machine takes a colonoscopy, high-resolution image of your colon and sends it wirelessly to a patch you wear on your back. It's made by CheckGap, and it's available in Europe and soon in the U.S.
Amazing.
So one thing that I want to add to what Alexis said is like, space, the rad hardness of GaN is really good. I mean, compared to existing silicon technology. And in fact, Alex, your company has shown some very good data on that. And what actually we are trying to do is also develop various things like monolithically integrated driver, so that you can not only use GaN as a power stage, but also you can integrate the driver on GaN to get the same radiation hardness. So one of the there's a lot of activities going on developing not only just a power stage or the driver, develop various circuits in GaN, which will make it radiation hard, and is very critical for deep space. For the LEO orbits, maybe is not that much radiation, but when you are going on a deep space exploration, you need very high radiation tolerance. So and GaN will be a key technology for deep space exploration, and also these integrated devices in GaN, various flip-flops and level shifters, and all these various sub-circuits that we are developing in GaN will add to that value of radiation hardness, not only in the power stage, but in the ancillary circuits.
Thank you, Amit. Let me see. The next question is coming up. How does integration help with issues such as reliability and cost in 650 volt GaN domain?
Yeah, so maybe I can answer this one. This is Robert from Texas Instruments.
Yeah, Robert, go ahead.
Yeah, please. So TI's GaN offerings all contain integrated drivers and various other circuits that kind of help with reliability. So our devices contain over temperature protection, over current protection, over voltage protection, and all of these we're able to integrate and help to make the device more reliable. In addition, by including the driver with the GaN switching device, we're able to make it easier for the customer. So it takes issues such as layout, parasitics, other things kind of out of the equation for the customer. So being able to integrate and have these features is really a benefit that we see.
Thank you, Rob. We can go to the next question. How do they compare with CSP regarding soldier joint reliability thermal cycling?
Yeah, I think that's in reference to wafer level chip scale packages. EPC has recently introduced 2 years ago, introduced package parts in these PQFNs, and the reliability in terms of thermal cycling and temp cycling is about the same as a chip scale package, with one additional benefit, and that is in the PQFNs, there are wettable flanks, and when you have a wettable flank, you can inspect the solder joints and make sure that they're all perfect, and that gives you an added confidence that you can get full benefit of the temp cycling and thermal cycling capability.
Thank you, Alex. The question is, can I apply underfill if I need longer lifetime?
Yeah, so EPC has done extensive studies of the effect of underfill on temp cycling capability, and they're available, by the way, in our Phase 15 reliability report, which is on our website. And we actually have the physical models of stress and strain. And we give parameters for selecting the right underfill for your device, whether it be PQFN or chip scale, wafer level chip scale, or anything. And we've shown that you can extend the lifetime in temp cycling, particularly with a wafer level chip scale package, 100 or even 1,000x in terms of capability of number of cycles. So take a look at the reliability report if you want to see how underfill can impact your reliability. It's a very positive thing, but you got to select the right underfill.
Thank you, Alex. So we're waiting for more questions. Here we go. So will you make these products according to the automotive requirements in the future? Will that mean any significant changes?
We already have about 20 of our parts that are AEC-Q certified, and we intend to certify any device that has a meaningful automotive requirement. Our process is completely capable of it.
Thank you, Alex. We have no questions at that point. I just want to come back, as I'm very interested to see what a vertical GaN would do on the market. Any comments for vertical GaN on your sides? Okay, gentlemen. I have to look forward to PCIM to see people who are fighting on that subject, and so far the next question is coming.
So,
can you elaborate on the parallelization of GaN for high current applications?
yeah, so we have many applications that do high parallelization of GaN devices. One of the big examples that you may guess at, I guess, is robotics. In some of these humanoid robots, they have 24 GaN devices in parallel, in a three-phase motor drive that allows these robots to do flips. And the reason you can do this is that GaN doesn't have something called a Spirito effect, which plagues MOSFETs and IGBTs and impacts the parallelability of those components. So in a MOSFET or an IGBT, there tends to be a current hogging that can occur. In parallelization, in GaN, it tends to be self-regulating. So you can put many in parallel and get a very stable performance.
Okay,
Also,
Alex?
one more quick comment is that being a lateral device is much easier to parallel also sometimes. So sometimes it's actually GaN devices are a little bit easier to parallel than, for example, power MOSFET, which are kind of vertical device. That's also one advantage.
Yeah, I would say we've also had a lot of success with paralleling GaN devices. So whether it's discrete devices from EPC, we've done plenty of paralleling those with our own drivers. And in addition, we have our integrated devices, which we also parallel. One of the main applications that we see GaN really kind of pushing forward in the future is in the server and data center space. So with the server and data center space, the power is going up in a lot of these server racks, and the efficiency for the power supply needs to be increased. And one of the only ways to get there is with wide bandgap devices. So it's a real kind of chance for GaN to really step up in that application.
Yeah, on that, Rob, I'd like to just show this is kind of the latest server DC to DC converter. It's an LLC converter. It's made by Syntec, it's made by Flex, and it's made by MPS. This is 1,000 watts. And that's 5,000 watts per cubic inch. And this is heavily parallel GaN devices. Right? You can see them on one side, and you can see the parallel ones on the other side. I mean, it's all paralleled here. And this works, again, at 1,000 watts in very high density servers. So parallel and GaN is straightforward.
Okay, thanks, gentlemen. Let's see. Will we ever see 1200 volt GaN on SI?
I mean, maybe I'll start. I don't want to say that we'll never see it, because somebody's going to come along and something's going to happen. But there's definitely limitations to it happening right now. In terms of the devices and investigations that we have, we don't see it to be commercially feasible right now. But that doesn't mean it's not going to happen in the future. I never want to say never.
Yeah, I mean, I think Visic, the Israeli company, already has them. I'm not sure whether they're in production, but they've certainly been talking about them.
Okay, gentlemen. I see the next question coming in. And I think what about the substrate on GaN monolithic? Is silicon the right solution?
So maybe I'll start on this one again. So we've done extensive studies, and based on our designs, we feel that GaN on silicon can become cheaper than high voltage silicon switches by 2025. So I think putting the GaN on silicon in terms of manufacturing processes that are available today is really the right choice. It's going to drive the cost way down as the yield improves and as we are able to get enhancements there. Like I said, by 2025, 2026, we believe that the price of GaN will be less than the price of silicon for high voltage switches.
You know, I think that the issue of ICs is also an issue. EPC has GaN ICs, including fully monolithic power stages on silicon. Silicon's a great substrate for that, for exactly the reasons Rob said. It's cheap. It's available in a whole variety of flavors. I think as you go to higher voltages, the challenges increase, and you may need to go to either manufactured substrates or silicon on insulator, in the 650 volt range, if you want to have a multi-power device integration. If you just want to put drivers on FETs, you don't need anything other than silicon as a substrate.
Yeah, I totally agree, Alex. But essentially, it's the cost. I mean, all these other substrates. I mean, there are other substrates which could be better, but the cost is quite a bit more. So, and the power industry is very sensitive to cost. So overall, keeping the cost in mind, I think GaN and silicon probably the way to go.
Okay, thank you, gentlemen. Here we go.
I'd like to make one other point about cost. Is Rob, you said in 2025 or whatever the cost would go lower. At APEC, we ran a challenge at our booth to find parts that were lower priced than our GaN devices, and 65% of the people failed at that, and 35% succeeded. But they succeeded with devices that were 40-year-old MOSFETs. So GaN is already cheaper than silicon, and I don't want to leave any doubt about that, because if so, come on, bring it on. We got challenges on our website. You can find cross references that'll show you all the prices out there in the market.
Okay, Alex. Paralleling of GaN is relatively easy for some size devices. How to balance if switches are not of same sizes? That's a very unusual question, as I never in my life had seen paralleling different sizes of devices. That's a 1st of April question.
Yeah, I'm not sure why you would want to do that. But I think, well, yeah, I don't know why you would want to do that.
There's no reason. There is, to me, no reason putting different die sizes in parallel.
I mean, the only thing that I can think of is if you put the devices on the same heatsink, then they're going to be the same temperature, and naturally there will be some power balancing of the devices, but it doesn't seem like a great idea.
Well, so again, it's a theoretical discussion in some ways, but interesting question if you're doing current mirrors. Where you have an imbalance, right? You have a small device current mirroring a larger device, and they're essentially running in parallel. We found that works fine. I don't think we've tried it in all configurations, but it works pretty well. And I think it's because GaN devices parallel very easily. They don't have these weird, unusual effects like in MOSFETs.
Yeah, it's kind of self-limiting. That's the beauty.
So, but from an engineering standpoint, I would not go and recommend people to do it just for what kind of reason.
Yeah, I
To me,
can't imagine
there
that
is
you would
no
go and
reason.
put like a 1 milliohm device in parallel with a 10 milliohm device.
Like I said, in current mirrors,
for current mirror, yeah, I think it makes sense.
Okay, yeah, Alex, you're right for that. Use it.
Bodo, I saw one earlier that we didn't get, and I want to know the answer to it. So maybe I'll ask the question. It was earlier about a two-dimensional electron gas in vertical GaN. I'm not aware of there being a two-dimensional gas in the vertical direction, but are there configurations of vertical GaN that allow for that?
I don't.
I was hoping Amit had some insight, or Rob.
No, I have not looked at vertical GaN That well, are you referring to something like a FinFET type of thing, meaning like a lateral, sort of a vertical channel?
Sounds interesting.
No, but most of the time, what I have seen is essentially almost the same as. So you have like a drift region, right, in GaN, and essentially that's supporting the voltage. So more like a bulk thing. But there might be that it's a new area, so there might be device structures which I'm not aware.
And it's a big disadvantage of vertical GaN because the mobility of electrons in the vertical direction is essentially the same as silicon carbide, so you don't gain any big advantage in resistivity.
Okay. Thank you, Alex, for the. Can you elaborate on GaN capabilities to block negative voltages?
Yeah, I'm not sure if the question is looking at bidirectional switches. You know, negative voltage is kind of an unusual question, or maybe it's talking about P-channel devices. You know, the ability for GaN to block voltages is quite good, and it comes from the fact that there's a tighter chemical bond between gallium and nitrogen than there is between silicon atoms in a lattice. That gives you a higher critical electric field, 3.3 versus 1.1, which that's the critical field, which gives you a 10x ability to bring two terminals together without them arcing inside the crystal. And that's one of the big benefits of GaN over silicon, is that you can make the devices closer together for very high voltages, which means the electrons don't have to travel as far. If you add to that the two-dimensional electron gas, which gives you you know, maybe a 3x advantage over the mobility of electrons in a MOSFET, you get a huge potential, about 6,000x advantage in terms of die size for the same voltage, and on resistance. And that's the advantage of GaN. So it comes from ability to block voltage, and then that shrinks all the dimensions that are in the resistive path, and then that allows you to make much, much smaller devices.
Okay, Alex. My backstage says there is no question at the moment. So
just one more thing to Alex's point. We talk about the resistivity being a big advantage because everything's closer together. The other big advantage of GaN that we see is the reduced capacitance. So the COSS of the devices, again, because of those tighter bonds, able to put things closer together, you really reduce the capacitance. And that's where we see a lot of the advantages over silicon is in terms of the switching performance.
Yes, that's exactly right.
Yep.
Thanks, Rob.
what's the benefit of GaN to be used in 500-volt powertrains? Amit?
Yeah, so basically, I guess you're referring to the EV with the 400-volt battery, or is this different?
The question comes from the auditorium from outside, so I have no reference at that moment. It's automotive, yes. The auditorium confirmed it's an automotive question.
So what we basically are looking at, you know, like a 400-volt battery system, like 400-volt bus, and then you have essentially with all the various overshoots and all, maybe we need to be robust, let's say till about 520 volt or so. So a 650-volt device is pretty good. I mean, that's what it gives you enough margin. Now for 500-volt bus, you have to take into account overshoots and all. So that needs to be looked at. So you probably, and essentially one probably needs 700 volt devices, which are actually becoming available also fairly soon. So I don't anticipate issues using GaN in the 500 volt range. And the advantages are the same as we discussed, all of us, that you have basically a better efficiency, lower loss, and you can make the size smaller, right? That's pretty much my take on this.
If there are no more questions, I like to thank you for the tech talk we did on wide bandgap, which is always a pleasure for me to have you on a quarterly base based on the articles published in my magazine and addressed to the auditorium. You can track anything in the magazine, the articles, and our tech talk will be later available on YouTube to review. Whoever wants to see it, who had not the chance to be on time with us here. Thank you so much. Looking forward to PCIM in about five weeks. No less than 5 weeks, 4 weeks. 4 weeks.
4 weeks.
Time is moving so fast. Okay. So enjoy the day when the sun comes out, and we'll have a great day, and goodbye, gentlemen.